Hello everybody and welcome back to another video by Funlearn Tutorials. Today's video is a rather interesting but small exercise that we'll be doing on prisoner's dilemma. So a lot of you, well some of you I hope, might have been looking up game theory and they might feel, well, I did look up a few game theory matrices and what I found out is most of them have positive numbers and this one has negative numbers. So I just said in my previous two videos that this is a very basic structure of game theory and it has wide applications in game theory. So if a prisoner's dilemma matrix has wide applications, why does it look so different from the other matrices? The main difference might arise from the fact that this has negative numbers, whereas pretty much all other game matrices or all other widely used matrices might actually have positive numbers. So what's the deal? Like, can these negative numbers be magically transformed to some positive numbers? The answer is actually yes. So these matrices can be converted to other matrices for ease of calculation, for ease of understanding, and that is what we'll be doing today. So today's exercise is sort of like an application based exercise where we try to convert the prisoner's dilemma matrix into a positive payoff matrix. So essentially the prisoner's dilemma has some negative payoffs and you have to sort of think, okay, well, a small negative is better than a large negative, and make it a little confusing. And what we'll be doing today is we'll be trying to convert this into a positive number matrix so that it's way easier to understand and analyze what is going on at the background or behind the scenes of the decisions made by the two prisoners. So we have the same strategy. So both the players still have two things to choose from. So they can either confess. Well, let me just write that down properly. So player 2 can either confess or can deny. That's the usual thing that we came across in our last two videos. Need not be explained, or if you want, you can go back to the video. I will be linking them down somewhere, linking them down in the description box below, as well as connecting them somewhere up in the right corner over here. Similarly, player 1, what is happening with my computer today? So similarly, player 1 also has two strategies to choose from. He or she can either confess or he or she can either deny. Now, the magic happens here. We change the numbers in the cells so as to make them all positive numbers. Now, how do I do that? This is where we can think of it. So, a person can at most lose 9 years of their life in jail time, right? They can at most lose 9 years. So, if I am not losing any years, it means I'm actually saving 9 years of my life, right? So, think of it this way. I can actually think a zero payoff as actually saving 9 years of my life. I save 9 years of my life, whereas my friend here who denied when I still confessed saved 0 years. So he lost 9. Here the numbers are actually the years lost, whereas these numbers are the numbers of years, or the numbers of years. These are the years saved. So if I am a honest person and I confess, I save 9 years of my life. My friend here who tries to sort of get his way out and deny his crime ends up losing 9 years of his life, or saves none. He saves 0 years. Similarly, if I lose 6 years, whereas the worst possible scenario was actually losing 9 years, that is this minus 9, I actually end up saving 3 years. So my friend here also saves 3 years if both of us confess. The reverse logic from this cell can be applied here. If I end up making the wrong decision of denying, by trusting my friend, I save 0 years of my life because I have to spend 9 years of my life in jail. Whereas my other friend who actually sort of switches out on me, will be saving 9 years of his life, that is he lost 0 years. And here the worst situation being losing 9 years, each of us are saving 8 years of our life by actually losing only 1. if you apply the same logic that we applied in our previous video, so again the video will be linked somewhere up in the description box below, up. So suppose I am player 1 and I have reasons to believe that player 2 will confess. So I can either confess and get 3, or I can deny and get 0. Again, remember that these are positive payoffs. Positive means good, 0 means neither bad nor good. So it's a standard way of comparing two numbers. So player 1, suppose player 2 confesses, player 1 sees, okay, 3 is better than 0, I should confess. Suppose player 2, suppose I as player 1 have reasons to believe that player 2 denies. If I confess, I get 9. If I deny, I get 8. 9 is better off than 8, so I'm better off as confessing. So again, confess is the dominating strategy. If you forgot about dominated and dominating strategy, I suggest you look up the previous video. It's simply sort of like dominating, sort of like whatever the other person does, I'm better off doing this. So again, let's now fix the strategies for this first player. So if I'm the second player and I have reasons to believe that the first player will confess, I look at 3 versus 0, I'm better off playing confess. Similarly, if I have reasons to believe that player 1, which is prisoner 1, will deny, I compare confess payoff 9 with deny payoff 8, and I'm still better off playing 9, which is confess. So again, this comes out to be the Nash equilibrium. So the result does not actually depend on the numbers themselves, like the absolute numbers. Rather, it depends upon the orientation, the way in which numbers are arranged. The numbers are such that actually the Nash equilibrium is not the best possible outcome. The outcome which can never be achieved, these are never chosen, right? The deny options are never chosen. Still, this option is somehow chosen. This option is somehow chosen. There are some ticks marks in the cell, but this does not have any tick cells. These are never chosen, but this is actually the best possible outcome. This also tells us something about the real society. It says that we might actually overlook the best possible outcome sometimes. Sometimes we think, no, that is the worst possible outcome, but that is actually the best possible outcome. So this is sort of like a real life application of game theory, and that is where the subject of economics is actually the most the beauty of economics lies in the fact that you can actually extend the applications and the concepts and logic of economics into real life and find out that the real life is not actually very different from what the economics books portray them to.